This vehicle relies on aluminum balloon tanks to go to low Earth orbit. And again, it's crazy to see, but every time there are visitors coming to the facility, the thing that I like to basically show them is that they can lift the tank on their own completely. And it's probably the very first time in spaceflight history in which you can hold an entire propulsion system of a rocket in your hand, because it's almost 10 kilograms, more or less, and the entire tanks of a vehicle in your hand, because they are pretty 15 kilograms in weight. And we have already tested them under pneumatic condition and cryogenic condition. We fill them up with liquid oxygen already, and we already test tank pressure that we're using for the vehicle. So crazy the fact that are 15 kilograms in weight, yet they withstood basically more than 50 tons of force in every direction just for the pneumatic pressure inside. We are creating the first single stage to orbit, hopefully, that is going to fly in a couple of years. And it's going to be what we call the personal computer of a space vehicle. We are trying to create a space accessing technology that is small enough and simple and cheap enough that can be used to open, let's say, accessing to low Earth orbit to a much wider variety of people and public.
Welcome to Next Big Future. I'm very glad to have CEO and founder Matteo Barbarossa of Italy, who had a radical new approach to spaceflight with radically cheaper $100,000 to orbit, single stage to orbit rocket. Welcome, Matteo. Please describe what you've been doing there at Sideris Space Development.
Yeah, here at Sideris, a company that I founded in 2019, we are creating the first single stage to orbit, hopefully, that is going to fly in a couple of years. And it's going to be what we call the personal computer of a space vehicle. We are trying to create a space accessing technology that is small enough and simple and cheap enough that can be used to open, let's say, accessing to low Earth orbit to a much wider variety of people and public, much like a personal computer did with computing in the 70s.
And you've done this without creating radical new technology, but you've taken what exists and simplified the launch vehicle, lightened it up, gone from 2 stages to 1 stage, and also have simplified the launch facility, the launch environment, launch tower.
Yeah, exactly. Basically, single stage to orbit has always been considered the chimera spaceflight, such a, let's say, difficult creature to achieve. But most of the issue, and also one of the reasons why we decided to go for them, it's that creating the personal computer of a space vehicle requires, let's say, a minimal logistic kind of infrastructure. So if you are intending to create your reusable launch vehicle, you either do for a fully reusable 2-stage to orbit, but then it gets very easily complicated in terms of heat shielding and re-entry from orbit with a much smaller vehicle. So the logistics associated with developing a 2-stage to orbit were increasingly more complex than the logistics of a single stage to orbit, while the vehicle, of course, it's a bit harder to develop because of the mass constraints of single stages. But really, the major thing here is that there are no groundbreaking new technology that has been needed to develop else, because it's pretty much single stage orbit are as old almost as the entire spaceflight industry. The very first Atlas rocket, the ballistic missile, was actually 1.5 stages and was mostly constrained by limitation in material science and rocket engineering back then. Nowadays, we have access to much better technologies, much better materials, and hence single stage to orbit are simply impractical for the current use of launch vehicle. But in the moment in which you reframe it to easing the logistics of accessing to orbit, which is the key here, then they become yet unpractical but extremely effective in achieving their job.
Why don't you share with us some of the images and things that you're working on?
Okay, now you should be able to see the screen.
Yes, we can see it. Thank you.
Perfect. So what we're trying to create is what it's been basically the fantasy of, I think, the last 60 years of spaceflight, or even more. Basically, we're trying to create a way to achieve low Earth orbit with much easier times compared to the current technologies, even though without trying to reinvent the wheel again. As I said, there's no warp drive here. The key point is that it might not seem like much, but accessing to low Earth orbit is almost as hard as getting to everywhere else in the solar system. So nowadays we mastered pretty well accessing to low Earth orbit, but yet, if you think about it, most of those kind of rocket launches are still kind of a novelty. SpaceX is doing a great job in bringing them to the daily life, but we are still far away from, let's say, getting your rocket to move from Sydney to New York, or from Rome to basically anywhere else on the planet. And the key point here is that making such a future is not just something that will ease our life, but it's if we want really to expand into the solar system, if we want to really colonize the outer planets, if we really want to go there, the first step is always going to be low Earth orbit. So until we make low Earth orbit as accessible as every other places on the planet Earth, we are still not getting the interplanetary civilization we're looking for. So what we're trying to create are technologies which enable for this kind of activity. So this kind of simplicity in accessing to space, which doesn't necessarily mean making the rocket much more efficient, making a nuclear-powered rocket or something like that, but it means shifting the focus from developing technologies to make the rocket better, to make the rocket easier to use. And that's where basically the key stands. And as I was mentioning to you, single stage to orbit, which is probably one of the technological key we are bringing ahead in development, and have not been, let's say, pipe dream, because really the very first vehicle capable of putting a man in low Earth orbit from the United States was basically at 1.5 stages to orbit. It just dropped the engine to reduce the mass along the way, but nowadays we have the, let's say, mass optimization possibilities to not do that. And what we're bringing to life, and what is coming up to life, it's this is what we call the personal computer space vehicle. And it's called Asos, like the Greek god for the dawn, to signify, let's say, a new way, to approach to space exploration. And it's a very, very small rocket. It's actually by far the smallest rocket everybody has ever seen, probably. It's just 4 meters tall, 4.5 meters tall. It can bring us very small payload. Again, we're not reinventing the wheel and making a rocket so small requires a given penalty, which is making payload capability only for 10 to 12 kilograms, so 6U more or less CubeSat to low Earth orbit. But it's meant again as a personal computer. So your personal computer for sure does not have the same computational capability of a supercomputer or standing in a university center or something like that. But nevertheless, it's a very useful and very powerful tool because it can distribute computing power worldwide to billions of users, not just to a few very specific users. Much like basically Asos, so much like Asos doesn't have such a high payload capacity, but it might provide orbital access capability from basically a concrete stand, 1 kilometer area where you can launch from. You don't need infrastructure. You can launch to orbit, deploy your payload, return from space, and recover it. Again, without using any new kind of technology for that. This to give you a scale of comparison. This is Asos compared to a Falcon 9. So you can see that basically the difficulties involved in making this rocket are much more comparable to the university student team sounding rocket compared to a Falcon 9 in terms of scales.
So for those, go back to that previous slide, just so people could see it, they may have missed it. It's beside the Sidereus rocket is beside the car near the bottom. It looks like a small bullet relative to the other larger Falcon 9 rocket. So it's far
smaller than... It's smaller than the Dragon capsule. So you can actually launch it on a Falcon 9. And once you get to low Earth orbit, because it's only 2 tons in weight, it burns kerosene and liquid oxygen. And it has an ISP also that is not really great. So the performances of this rocket aren't really the best you can find around. Actually, they're not really great. But still, nevertheless, if you were to carry it to low Earth orbit, and Falcon 9 would be more than plenty to carry, I think, up to 10 of them, then you would have enough delta V to reach Pluto, Neptune, or whatever other outer planets that you're looking for. So
and it's literally the size of a car. So 2 tons is about the size of a car. It's about the length of a car. So go ahead to the next slide, Tim.
Yeah, so this to give you a scale of comparison to the engines of a traditional launch vehicle. Actually, not so traditional, but these are the Raptor engines from SpaceX, and hence the rocket that we're creating is smaller than those engines. To give you an idea, in terms of weight, it's 2 ton fully fueled, but 30 kilograms when empty, plus 12 kilograms of payload. So it's basically lightweight enough to be carried on a shoulder by 2 people and be set for a launch. Again, you have to imagine it much like a sounding rocket made by a student team compared to a normal rocket, but with enough delta V to reach low Earth orbit in a sun-synchronous orbit from every place on Earth. And the mission profile is pretty straightforward. It's not different from most of the rocket, with the only difference that there is no stage separation, so you don't have any stage falling along your trajectory, and that's another important key. Because most of the rockets, and we also evaluated that to go for a 2-stage to orbit configuration, of course, in the very first place, not to make our life any harder than already would have been. But the key point here is that if you think about launching from every place on Earth, and when I say launching from every place on Earth, I mean that the rocket itself, it's meant to be launched from, as I was mentioning, from a concrete pad sitting somewhere on basically just with 1 kilometer of radius away from the launch site itself as an exclusion area. 2 tanker trucks, one for liquid oxygen and one for Jet A, will be able to fill it up with propellants. And then completely remotely using an architecture that we call a laptop and launch. So just one laptop station to control it, and telemetry being provided by satellite telemetry and downrange telemetry. We can control the entire vehicle. So we can perform the payload integration directly on the pad, fill it up with propellant, go away from the vehicle, launch it, send it into orbit, and then from there there will be an autonomous reentry, splashing down with a parachute in the ocean. And it's important that making it a single stage to orbit in this perspective, because what if something goes wrong along your trajectory? What if you're few seconds after while you're in flight, your engine shut off? It's a very likely possibility, especially if you're imagining to launch not 10 vehicles a year, not 1,000 vehicles a year, but maybe tens of thousands, of course, in a very far future. But if you're imagining to basically launch much more frequently than any other launch vehicle, because you are much smaller and you're intending to really provide a much more frequent access to low Earth orbit, then making the vehicle safer is a need. But we know that space is not really kind with technologies, it's not really, let's say, the softest environment to work with. So making a rocket safer, it's a process that can be done, but requires, like for aircraft, requires tens of years, requires a lot of studies. What we decided to do is not to avoid failure whatsoever, if not as much as we are doing pretty much whatever other rocket companies are doing to mitigate failure probability. But in the case a failure will occur, we have parachute landing. So we can simply shut off the engine, vent out the propellant, and bring it back using a parachute. And this is not really something that you can afford with a 2-stage. If you're not staging in the right moment, you are not going to survive, and you're going to make debris fall on people, which is, let's say, a dangerous activity. So we are intending to develop a vehicle which can be launched also from inland, which doesn't require the same downrange of traditional launch vehicle, which can mitigate a lot of the risk probability for those kind of things. And to develop this kind of vehicle, we are basically spending a lot of time and resources in our test infrastructure. This vehicle is completely being designed in-house. It's completely going to be built in-house. We are building it in-house, and it's completely tested in-house so far. We have our own test range here in Italy, near Naples. We have our own facility here, and we are testing our own rocket engines, completely developed in-house, the MR5 rocket engines. Those are basically 3D printed completely, are region cooled with kerosene Jet A. And for example, we decided to go with Jet A propellant instead of RP1 because Jet A is much more accessible. So if you want to launch from somewhere, you don't need to basically buy rocket propellant from a very specific site, but you can use your local supply of aviation fuel. And liquid oxygen is commonly available in every supply chain, so you don't have to basically talk to anybody specifically to get your propellant. And it's basically a very small engine. Is pretty much the size of 30 centimeters, in the ballpark of 30 centimeters of a large water bottle, but it can generate 2.5 tons of thrust, and basically It can push the vehicle up to 28,000 kilometers per hour, which is pretty fast, but it's what is needed to get to low Earth orbit. And these are the test infrastructure that we're building. We have the philosophy of breaking things fast and basically get ahead, because, of course, developing these kind of technologies requires a good amount of, let's say, trial and error, especially if the team is young, especially if there are, let's say, less resources compared to other projects. We have gathered so far 7 million euros to develop this vehicle. And we have already proven that the propulsion system, the structures, which were, let's say, one of the most critical aspects of it, let's say, everything else has been basically already packed up. And indeed, we have created the first balloon tanks. This vehicle relies on aluminum balloon tanks to go to low Earth orbit. And again, it's crazy to see, but every time there are visitors coming to the facility, I think that I like to make to basically show them is that they can lift the tank on their own completely. And it's probably the very first time in spaceflight history in which you can hold an entire propulsion system of a rocket in your hand, because it's almost 10 kilograms, more or less, and the entire tanks of a vehicle in your hand, because they are 15 kilograms in weight. And we have already tested them under the pneumatic condition and cryogenic condition. We fill them up with liquid oxygen already. And we already test them under the basically tank pressure that we are that we're using for the vehicle. So it's crazy, the fact that are 15 kilograms in weight, yet they withstood basically more than 50 tons of force in every direction just for the pneumatic pressure inside. And these kind of technologies are, let's say, were the most difficult part to achieve. But in a couple of years, we started in 2019, but actually we got enough resources to start the research and development in 2022, the beginning of 2022. And as far as right now, we are basically in May 2024, we have achieved lightweight enough balloon tanks. We are in the ballpark of 20 kilograms, still a little bit of mass optimization yet to be done. We have a propulsion system that has been tested successfully, that is extremely lightweight. The chamber is just 5 kilograms in weight. We have basically on a very good path to do a first low altitude flight by the end of the year, and basically a suborbital flight by the end of next year, so that we should be settled for a first orbital flight by basically 2026, more or less.
Amazing work, clearly on a shoestring budget, because literally the entire your $7 million funding is less than most single-use rockets launches. Like I think Rocket Labs tried to go for like 5 million. I'm not sure they hit that target of 5 million. And DARPA was looking for those kind of prices. So to get the entire development of a rocket system and its launch facility, which is basically, you had showed the pictures of working out of 2 sheds. So I'm in Silicon Valley, and you talk about the PC revolution, that the first computers like Apple famously coming out of the garage, and like you're coming out of the sheds, to lower the cost and to enable this breakthrough. And also, it looks like that. So not only will you democratize the access to space with costs down as low as $100,000 per launch of a 6U CubeSat, which is less than a rideshare mission. SpaceX rideshare mission, $350,000 per rideshare for 50 pounds of payload. So you're in that range, but with a payload, but with a cheaper system. And basically you can enable the universities, a rich community college to have their own space program, that they can spread these rockets everywhere. Like you said, the PC, basically, that you can go anywhere with that. Just
yeah, if you think about it, basically it's just like what CubeSat did back in the days. Basically, CubeSat allowed for the first time to get an entire satellite being controlled by a university group. And yet with CubeSat nowadays, that became the favorite platform, especially for low resources entities, companies, universities, groups of amateurs to basically access space. Yet they never became the widely used, popular swarm of satellites into low Earth orbit. But yet we are flying hardware in some satellites, which is at least a decade decade old. One of the key problems that we still have, for example, for space exploration is that even though we managed to basically push extremely fast for getting to low Earth orbit with, let's say, lower and lower threshold for everybody, we still are using very limited technologies, because nowadays, as you pretty much what you have said, an entire Electron rocket launch costs in the ballpark of 7 million. So the entire funding that we had so far to develop Asos, and that, however, for us, managed to build the tanks of the vehicle, build the propulsion system of the vehicle. So basically, the key point here is that threshold has been getting lower and lower for everybody, but yet the technological advancement has always been limited by one major constraint, which is time to go to low Earth orbit. Especially for smaller satellites, getting to low Earth orbit nowadays takes basically still anywhere from 3, but much more likely 6 months to basically 2 years. And small payloads aren't really the priority of anybody. Understandably, if you have a Falcon 9, you have to fill it up with 10 to 20 tons of payload, not with your 12U CubeSat, 6U CubeSat, 12 kilograms of payload. But the key point is that with smaller platforms can be developed much, much quicker compared to basically a big platform. And that's a key advantage, a key point, because a small platform managed to provide an extremely good way to test everything that you want to test, advanced technology. You are not limited anymore. They cost basically they cost nothing or less to be developed, so you can be much more ambitious. But if you are still constrained of waiting 2 years to see your project in orbit and demonstrate your technology, your costs are still going to skyrocket. So it's much more worthy to stick with your garden variety technology around. If we develop a vehicle which can be sold to basically companies, to universities, a vehicle that is not held by a single company, but that is decentralized, everybody can operate it potentially. Of course, not everybody, understandably, for the consequences that it might have. But basically, if a much wider variety of people and groups can operate it, then it means that accessing to space is not a matter of years, but is a matter of weeks. And getting down to weeks to get to space to test your project becomes much, much more similar to the times of development of this small platform. If you had the ability to launch your 1-ton satellite every 2 weeks, it wouldn't really matter to anybody. Nobody develops a 100-kilogram satellite in 2 weeks. Maybe you have some spare and you need quick response to low Earth orbit. And for these reasons, there are the quick responsivity program out there. But the key point is that satellites aren't built that quickly. And be that quick is especially needed when you have a smaller platform. And getting a small platform that is extremely cheap, potentially, that can test very ambitious technologies, advanced propulsion system, new communication, can allow for not only in terms of competitiveness for companies to be an order of magnitude more competitive compared to basically any other company, because you can launch in a couple of weeks what will take your competitor a couple of years. But also in terms of challenging the technological development, speeding up the technological development in space, because if you can test your advanced propulsion system at no cost, in no time, with the same cost of more or less a laboratory experiment, then it becomes extremely more convenient to directly plan a mission and launch it in low Earth orbit. Nowadays, we have CubeSat which are interplanetary, like the Marco CubeSats or the Argo Moon that has been launched a couple of years back. Those kind of CubeSat, yet they are launched in an interplanetary mission and they are just a piggyback. But we have nowadays technologies to push CubeSat from low Earth orbit out in deep space. And what could be like if we have a vehicle that costs so little that can allow for even missions that are so ambitious, like sending an interplanetary CubeSat from low Earth orbit to be made. You can drop also the price of space exploration down to a fraction of what is nowadays. And I'm sure that this kind of trend is going to increase, not because I'm faithful of the product we're creating. That let me say, I don't really like to call it a product, because it's a technology that we're bringing to the world. Asos is not Eos itself, it's the single stage to orbit, it's the miniaturized SpaceX. Eos is basically what we think it's going to be the future of spaceflight. And if you can get a vehicle that is that small, you can enable space exploration, ease space exploration. miniaturization is ongoing, and we can't deny it, with processing power getting smaller and smaller, with basically capabilities that can be all more and more squeezed into smaller packages through origami deployment technologies or those kind of things. So lowering down the threshold also to get to space is what I was mentioning in the beginning. Low Earth orbit is your starting point for everything. And if getting to low Earth orbit still takes years, you're going to think twice before launching an advanced project. But what if basically go to low Earth orbit could be like basically a laboratory experiment? Then you might not think twice anymore, and you might speed up then this kind of technologies.
So as we saw, you actually have the hardware, you have the engines, you have the tanks, so it's all been made. Also, for people who are not aware, all the trends for the space industry on the satellite side have been going from, billion-dollar NASA satellites, $2 million NASA satellites, to $100,000 CubeSats. The Starlink satellites, of which there are 6,000 in orbit, are down to about the price of $250,000 to $1 million. You can get to mass-produced satellites, full-size small satellites, in the $250,000 range, and the CubeSats can be down at $50,000 or even less. And the 60 CubeSats that you're looking at, this is clearly the launch system that is aligned with the trend toward CubeSats. So you can mass produce CubeSats at very low cost. Like, people can make a platform of like, here's everything for a CubeSat, and then just add in the actual mission part of the component. So then, just like, let's say PCs, that everyone makes a PC, and then you load on software, load on some peripherals on the basic PC platform. So the cost, again, launch and PCs aligned, and because you can see that the already demand for thousands of CubeSats, that this, where we drop the price, so your all-in project cost goes from $2 million with your launch down to $250,000, $200,000, and with mass production, perhaps even less. That the economics, the frequency, that all that would change with what you're doing.
Yeah, that's absolutely right. One thing that, for example, we're working on is not just to make Eos a launch vehicle. Indeed, we call it the space vehicle itself. Of course, we are now focusing in launching it to low Earth orbit. That's the hardest, most part, as you can imagine, and it's the thing that we are currently focused on. But the plan of development of EOS relies also on integrating in-orbit activities, in-orbit permanence, and re-entry from orbit. This means that basically EOS is a fully-fledged spacecraft. You can use attitude control, you can use onboard power, you can use basically orbital maneuvering capabilities, you can use re-entry capabilities to protect your payload and land it back. Those are all ambitious goals, but they are all based, as I said, on technologies that has been created. So it's just a matter of trial and error. And with EOS, you can imagine that the production cost is comparable to a car. So you can get a lot of mistakes along your way very quickly. And just to give you an idea, nowadays, to produce a set of tank, we need a couple of weeks to produce an entire set of engine. A single engine, we require more or less a couple to 3 weeks. So making an entire vehicle might take more or less a month. So if you can make EOS so dirt cheaply, and you can test them so quickly, then those kind of technological challenges are just simply obstacles to overcome. And once you do that, you end up with a spacecraft that can potentially be used to host whatever kind of payloads. So much like you were saying, you might not even need to make the satellite itself, the CubeSat bus itself. You might simply host your payload on board of the spacecraft, keep it in orbit for whatever time it will be needed for your mission, a couple of years, a couple of days, whatever it will be needed. And by the time you basically have completed, you can get back and you can recover it, you can analyze it, understand what went wrong, what went good, you can basically tune it accordingly and launch it once again, which is basically a degree of freedom that nowadays you don't have. And satellites can't really take the SpaceX approach to be launched into low Earth orbit, if not at a very expensive price and not with, let's say, unwanted surprises along the way. But with this kind of system, let's say, if you can arrange just to give you an idea, in the final configuration, we're planning to have EOS be ready for a launch in more or less 5 hours. So you can basically set up a date to launch it, set up launch it much like, again, a sounding rocket, but send it into low Earth orbit, deploy your payload, stay in orbit or return from space, and all of this with whatever payload will come. So if you need to test if you want to put a new communication system in orbit, laser communication, you want to test your advanced ion thruster, you want to test a very small transfer stage, you want to get a very, very rapid visual recognition of a specific site. You might launch your EOS with a camera on board, fly over your site, get images of that, and then re-enter on the other side of the planet, all of this in 40 minutes. So also point-to-point demonstration. This is something that you can very well do. It's a vehicle that is already meant to return from space, is already meant to go to low Earth orbit, and it's a single stage, so you don't have to worry about getting your first stage along with you because it's already there. So let's say that this is the degree of freedom that we are trying to bring to the world, much like you said, like a software, like a peripheral for basically your computer. You have the freedom nowadays to use tools like Arduino, Raspberry to build your own project. It's a microcontroller, it's a multi-use platform, and you can basically do pretty much whatever you want. Nowadays, rockets aren't like that. Rockets are just your step to space, and then it's up to you to deal with everything. With EOS, you have pretty much your spacecraft. You go there, you do whatever you want, and then you come back all in one. And it's not just because it's fancy, it's not just because it's new, but again, it's to push development and ambitiousness of technological project in space to an order of magnitude different level, to an order of magnitude faster and more accessible manner. Because the space exploration is done in small steps ahead. EOS again is as not so small, but is a step ahead. Let's say ambitious, but not so ambitious step ahead that can, however, allow to basically make space an environment like another, and that's the key step for every human activities beyond Earth. So what we are trying to, much like the personal computer allowed for the creation of internet, the opportunities that a versatile platform, a universal platform, given to a multitude of users can bring this time in space are pretty much, for me, I'm just limited to the knowledge, to my fantasy, to my imagination. But that's the key point. It's not going to be more about us, about Siderius. It's going to be about whoever else want to use it for their own purposes, of course, with, again, some limitation. You don't give your ICBM to your garden variety people out there. As every technological development, there are challenges to overcome, especially over the security and safety side. We are pretty aware of that. And indeed, we are planning to use the vehicle, or much like any other launch vehicle at the beginning, and then through pilot project integrated to an actual distribution, much like aircraft. But the key point is that it's no longer about a single individual, a single company, a single person. It's going to be about what other people can do, about what the community can do, what, this is the point, decentralization can do. And it's an extremely powerful tool that we have seen nowadays.
So some of the thing you've highlighted in a vision I want to bring out again was that you talked about the integration of the payload, the satellite, with the rocket itself. Because if you have tens of thousands of these rockets, then all rockets would have to have communications and have to have energy. Currently, if I was to do a rideshare mission, I would need to spend $30,000, $50,000 in order to get S-band, X-band communications in a component that would then go into my satellite mission. And I'm taking up weight, taking up extra cost, which I can't use the communication systems on the SpaceX Falcon 9 because that's only for the main rocket for SpaceX to use. All the 100 payloads in a rideshare mission have to all bring their own systems. But a lot of extra redundancy, extra weight that is wasted, not useful to me. I'm doing stuff where I need to communicate, and I have to have extra cost and extra weight going to that. While if I launch on Sirius with a 10 to 18 kilo mission, and if I have ownership or allowed to integrate with the rocket, as I'm the only customer on that rocket, then I can use the communication systems of the rocket to send things back. So electrical communication, that all the things that I need to bring if I'm going to do a rideshare mission are no longer necessarily needed if I'm integrating in with the rocket. So the 18 kilograms is actually more like 100 kilograms relative to a traditional shared rocket payload, because I have less available to me. Even things like the payload shell and other things possibly not be necessary. If I did not need to deploy, the rocket could stay closed. I wouldn't have to have my own box, the what we call the bus of the satellite. That weight could be removed. Then I have 18 kilos of purely active mission. So the actual amount of usable payload increases with the Siderius, correct?
Yeah, exactly. Again, we're not, let's say, putting any kind of limit to the freedom of this vehicle. This vehicle has been designed to launch from every place. There is no launch site limitation, and much like this, like the entire philosophy of the development project, also the payload has no limitation. We are planning to start with a rideshare mission, your garden variety CubeSat deployment into low Earth orbit, because that is what people are used to nowadays. People are not yet used to integrate payloads elsewhere. It's not a market that already it's been so developed, if not for a project like International Space Station, Space Rider, or those kind of missions. But it's undeniable that if you launch your 100-kilogram satellite, you have, as you mentioned, most of your weight on communication, on power buses, power management, attitude control, satellite bus itself, thermal protection, thermal management. All of those kind of things are needed anyway for EOS. Usually, you're not even considering about doing something like that, because your stage, it's if you're lucky and you are a very heavy satellite, your stage is bringing only you into low Earth orbit. But after that, it's not even meant to stay in low Earth orbit for any reasonable amount of time. With EOS, the major limitation that we have is that being just 30 kilograms, but having basically 1 square meter almost of cross-sectional area, your ballistic coefficient is extremely low, which is extremely helpful during the reentry, because much like a leaf, we can basically slow down very quickly, very high in the atmosphere. So we don't have the same condition of a space shuttle during the reentry, and hence our entry constraints are much, much more mild. But if you are doing activities in low Earth orbit, then your ballistic coefficient is gonna basically bite you back, limiting how long can you stay in low Earth orbit. But for very high orbit, not so. More or less 700 kilometers, you can reduce dramatically your decay time, and you already have your sail to re-enter from space, from low Earth orbit along with you. So it's another additional benefit for preventing space junk from building up. But yes, that's the key point, is that your payload bay is already a thermally insulated, thermally managed environment. Your rocket already knows how to maintain its attitude. It's needed to get to orbit in the first place. Already has an onboard power management system, already has onboard communication for a high data rate for video streaming, for telemetry communication. It's a very easy object to track, and that's again useful in terms of preventing debris from building up. And it's a reusable re-entry system, which is meant to return to from space in a way or another. So your satellites might not need to stay for 2 years into low Earth orbit for activities and then stay there for 25 years to wait for the orbit, but you can simply deorbit by the time your mission is over. And with your satellite on board, then you can do pretty much whatever you want. You don't need anymore all of those kind of subsystems, satellite bus subsystem, but you can either be released in low Earth orbit like any other satellite, and that's pretty easy, your Garland deployer, or you can simply be hosted in low Earth orbit. So maybe you don't need to basically be deployed, you need to re-enter from space, and so you are going to spend some time into the EOS payload bay, being exposed to space condition, and then re-enter from space. Or biological satellite manufacturing, payloads, plenty of activities. Once you're over, then you can potentially re-enter, or if you want to put a much bigger payload, much like you said, you don't even need to bother about the satellite bus. You can plug it to the vehicle, you use that, and you can stay in orbit for as much as you want. Nowadays, we are planning to stay in orbit for as maximum 6 months, after which, again, the ballistic coefficient is going to bite us back. The radiation environment becomes a little bit too extreme for our avionics. That is meant to be much like a CubeSat avionics for basically short duration more than long duration. But we are not excluding making specific mission profiles with specific radiation hardened equipment for customers that need to stay for longer periods in low Earth orbit. And let's say the thing that makes me always say excited about this project is that the avionics of Asos is comparable to a CubeSat. So in terms of both size, in terms of masses, in terms of basically complexity, which is a completely different level from whatever is flying nowadays on launch vehicles. And it also means that it's extremely versatile. Whatever you want to do, you are very welcome to do it. It takes nothing to be integrated, and you can launch it. And it's much like playing Kerbal Space Program. You know, it's I wouldn't strap any other EOS stages on the first stage, but basically much like having a CubeSat, your flexibility it's limited pretty much by the frequency you can get to orbit. But since you are already getting to low Earth orbit with your system, then there are no more constraints on the technologies you are creating, and that's the key point. Making a system that doesn't have the usual constraint, that is meant to be as universal as it can be.
And you also, a point that we almost skipped over, you did show that with the parachute, that this is fully recoverable. That you can, single stage, nothing's being thrown away. So it's fully and rapidly reusable from the get-go. And basically, when you empty the fuel, the entire weight of the empty fuel tanks and the engine is 30 kilos. So it's basically like a ruggedized balloon in that it will just kind of float on down and then be recovered. And because it's so much lighter and relative to its area, as you described, then it will come down in a far more light way. The recovery of the payload fairings of the SpaceX Falcon 9, which they've done a few hundred times, where the payload fairings, that part separate each half of the clamshell. Those probably are far more heavy than what you're doing, and they are recovered with parachutes that land into the ocean. So similarly, your recovery could be as simple as that, and then you can then relaunch each of your rockets.
Yeah, the key point here is that making a miniaturized vehicle and making a single stage to orbit is a perfect, and also with a very low aspect ratio, is the perfect recipe for dealing with aerodynamics as much as possible. It's basically like asking for problems in all sorts of reason, but also if you're, let's say, trying to take advantage of what you get, also getting some benefits which are completely, let's say, non-traditional. First of all, during the takeoff, as I said, we have a more or less a 1.8 ton takeoff weight, and the vehicle it's more 1 meter. To give you a scale of comparison, an Electron rocket is 12 ton in takeoff weight and is 1.5 meters, so it's not much bigger, it's not much let's say wider, but it's much heavier. So we get a penalty, an aerodynamic penalty because of this during the ascent, which is huge. It's an order of magnitude higher than the Saturn V penalty. We have almost 11 kilometers per second of delta V because of this, because we have to compensate for those kind of losses along the way. The real point here is that you are going to suffer a lot of aerodynamic penalties during the ascent, but all of those aerodynamic penalties are not doing anything but slow you down. And that's something you really want during the reentry. So making a single stage to orbit is also very helpful in this perspective, because during the reentry, you experience conditions which are comparable to having a ballistic coefficient of 2 order of magnitude, 3 order of magnitude smaller than your garden variety reentry capsule. So as I said, it's like throwing a rock or a leaf in the air. The rock is going to go for sure farther. And it's pretty much the same with EOS. During the reentry, we slow down much higher in the atmosphere. We experience conditions which are manageable even from a radiative heat shield that is, in our case, the nozzle extension. It's a very peculiar design. It's not any heritage from Philip Bono or basically other SSTO designer. We're not using aero plugs. They are not really convenient for SSTO in this specific configuration. That's another interesting thing. Our performance, it's mass optimized more than ISP optimized, and that's what we care about. But anyway, we are using the nozzle extension for the entry, let's say, heat shield. So it's already well suited for withstanding very high temperature, for withstanding pretty high pressures inside. And the interesting thing is that basically we skip on the atmosphere we're using the skip like the trajectory. So our vehicle, it's intending to basically slow down very high.
Do you want to stop sharing this main screen so we can see what you're holding there?
Sure. Sure.
Yeah.
Okay. And so basically our vehicle, it's meant to use a skip light trajectory. So we are intending to dip into the atmosphere at a very shallow angle, heat up the heat shield at more or less a couple of 1,000 degrees Celsius, and re-irradiate all of the heat away in space. And then basically do that a few times in order to basically dissipate the energy, the kinetic energy that your vehicle has along a very high and very long amount of time. So total power that is very minor. And this is very effective because we have a ballistic coefficient that, as I mentioned, is extremely low. Once we let's say do the last dip in the atmosphere and there is no more lift to let's say keep on doing that, we dive into the atmosphere. But at that point we have a terminal velocity that, to give you a scale of comparison, is 28 meters per second, 100 kilometers per hour, more or less 60 miles per hour, it should be. And it's basically slow enough to potentially withstand the ground impact if it would have been optimized for that. But of course, 30 kilograms doesn't really allow you to be a kinetic impactor on one side and be basically lightweight enough. So we rely on a guided parafoil to do the last bit of the way down. It's not easy, let's say, as much as it would have been with the Falcon 9 fairing, only because the kinetic energy goes, of course, with the square of the velocity. The fairing separation occurs the ballpark of I think a couple 20 or 30 seconds after second stage. So you are still quite slow. The Falcon 1 stage has a pretty, let's say, low staging velocity. So you are still very slow, and you have a very high coefficient of a very low ballistic coefficient. So you slow down very quickly in the atmosphere, but it's not that far off compared to the, let's say, the geometry, the masses involved. And interestingly, when you do the parachute landing, for example, we decided to roughen the vehicle for a sea landing, so a sea splashdown, compared to, let's say, more advanced entry technique with a helicopter or stuff like those, because we are preferring much more to simplify the system at some cost. It will cost us something. Everything costs us something, and ever will be. But if you do the right trade-off, the cost of, let's say, processing the seawater, it's much more minute compared to advanced recovery system. And with the guided parachute, you can also almost pinpoint landing, and we don't really need to care so much about precision landing. So it's extremely effective for our strategy. Plus, we originally thought about more advanced landing system. We thought about, let's say, more advanced re-entry. We are a small team. We decided to keep the team very small because we decided to move extremely quickly. And it's a team of extremely talented people. I wouldn't ask for anything better than what we have. Extremely motivated, but with the limited resources, time and economic that we have, what we are trying to optimize is effectiveness. So a parachute landing would allow us not only to be reusable nominally, but also off nominally. If your engine goes out, you really don't have any other option but either explode, that causes debris falling down on people, or land back with a parachute, which is perfectly safe in that condition. So it's let's say it's a payload price that we pay already.
So one last thing I'd like to say is that beside the fact that you're opening this up to everyone potentially with about $250,000 for launch and for the CubeSat mission, is that it enables for the cost of say a $25 million, small actual full rocket, that other group using your system could buy 100 launches with 100 satellites and have a constellation of communication satellites for the cost of one mission. And then also if you go to 1,000 satellites would only be $250 million, far less than it. So it takes the constellation aspect of things, the mass production of small satellites and small missions going out into the universe with ion drives, would enable this explosion of capability just by going simpler and cheaper.
Think about this. One of the major limits, for example, that small satellites nowadays have is optic resolution. Your satellites might be basically 10 centimeters in by side, for example, an Earth observation 3 CubeSat. So you might have a very small lens, and that limits intrinsically what's the maximum resolution you can afford. But nowadays there are technologies that can not so easily, but actually very easily on Earth, not so easily in space, deploy huge mirror into low Earth orbit. You can deploy mirrors using the same technique of origami deployment. There has been studies made by NASA about plastic mirrors. There have been, let's say, there are companies actually working on deployable antennas, which pretty much obey the same kind of rules. You can make a very big structure into low Earth orbit, starting for extremely thin material, so extremely lightweight and extremely compact scenario. But hence why nowadays aren't we seeing deployable plastic optical telescope or things like those? Actually, on one side, we are seeing them. If you think about, there are some intelligence satellites into geostationary orbit, which have antennas that can deploy almost 100 meters, something which will be unbelievable even for the biggest launch vehicle nowadays. So those are things that nowadays exist, but especially for small platform, they are seen as a way too risky as an investment compared to simply getting your bigger satellite. And or for example, getting advanced processing power into low Earth orbit. It's something that requires a lot of power, so it requires a huge solar panel to be deployed into low Earth orbit. And nowadays it's something that, of course, it's extremely limiting. Testing, for example, thin film solar cell into low Earth orbit, it's hard and it's potentially risky, so nobody is really willing to get into that direction. And for this reason, small platforms are always seen, let's say, not so good because of the limitation of the size. But the limitation of the size is mostly because of the deployment of bigger infrastructure. And the deployment of bigger infrastructure, it's limited by the will of risking compared to simply spending more for bigger satellites. If you can get this kind of structure tested in space very, very quickly, it becomes a lot more convenient to potentially build the constellation of satellites, which are a tenth of the price, 100th of the price compared to your bigger satellite. It requires 100th of the time to be developed. So you can basically cut by a couple of orders of magnitude your investment and your fixed cost as a company. You can deploy satellites which cover a much wider area of basically of space, of surface on planet Earth. So you can do a lot more things than a single big satellite can. And you can make them custom. You can basically decide for a specific mission. You might require infrared observation. You might require specific resolution SAR. You might require a lot of different specific things, which are very hard to predict beforehand, and that usually requires years just to be developed in the first place. But if you can basically get your lab testing directly into low Earth orbit, then you don't really need to get any of that trouble, and it becomes a lot more convenient. And so you can exploit much more than whatever we are doing so far, the miniaturized platform as a characteristic.
Yeah, if basically the satellite innovation, people wouldn't take the risk because they had to buy the equivalent of a Gulfstream airplane, business jet, $40 million, $100 million. Here, I'm flying in a Cessna, $200,000. I can take more technological risks on the satellite because now I get the savings. It's worth it to me because now I can, push what's happening because I have less money at risk, less time, less money. Everything shrinks down to where it makes sense to push innovation, like you're talking about with satellites, make them bigger, make them lighter, that have the capability. This has been super exciting. I know we need to keep talking and to have you on again. But I want to wrap up. If you have anything else to say, then go ahead and then we'll schedule one for next time, I think.
Just to say that basically this kind of we're trying to bring to the world also, as I said, an entire technology ways of doing things technologically of let's say an edge of being not too ambitious, not too little ambitious, so to take ahead this kind of development, also for others, also for basically satellites manufacturing and so on and so forth, also for basically even more ambitious project than what we're doing right now. But we believe, and I was telling you before, it's in the logo itself of the company, going ahead in small steps, but toward a very ambitious goal with a solid heritage at the beginning. So we believe that really that if we can, let's say, it's much like what has been for startups. If you can do a small investment that might or might not pay you off, but you can do it in such a number that at one point will pay you off, getting technologies in orbit tested very often, very quickly, with very little expense. When there will be that technology that is going to pay you off, it's going to be a radical breakthrough. And is what we really believe. Decentralization, community, and multitude is what has created the internet in the first place, and what has been the most powerful resources we had in the 21st century. So it's what we believe it's needed also for space.
Well, it's very exciting. It'll be a mass production age for space, for satellites and for space. So thanks for being on, Mattia. And then
it's been a pleasure.
I hope to keep talking again. And everyone, like and subscribe and join us next time. Thank you.